Well, so today I think we will discuss some more aspects of special relativity that have some direct relevance to what we're discussing in the context of the general theory. So one of the things that we talked about, which is very important, is this energy momentum tensor, T alpha beta of x, right? And in order to write down an explicit form so that we could play with it and derive properties of it, we looked at the energy momentum tensor for a single particle, right? And for a single particle, this was P alpha, P beta, divided by the energy times delta 3 of x minus x of t, right? And so this is one particle, right? And so one particle is described by a trajectory x of t, which, you know, maybe goes from point A to point B, right? And so on the basis of this simple expression, we were able to find out that it is symmetric. Right? It is a symmetric object. And so that means that T alpha beta is equal to T beta alpha. And so that means that it has 10 components. In 4 dimensions, right? So it's when a tensor is symmetric, it doesn't have 4 by 4, which is 16, but just 10 components. And in addition, it is conserved, so it means that d by dx alpha of T alpha beta of x is equal to 0, right? So it is a conserved quantity. And so that means that we can construct 4 conserved quantities. Okay. And the reason why you have 4 conserved quantities is because there is still that index that ranges from 0 to 3 or 1 to 4, right? So there's 4 conserved quantities, which contrasts with electromagnetism, right, by the way, because in electromagnetism you have d by dx alpha, J alpha is equal to 0, and then the conserved quantity is the J naught. Right? So in electromagnetism, you only have 1 conserved quantity. Here you have 4 of them, and so these are the quantities that you get by integrating in d3x of T alpha 0 of x. Right? When you take the naught component of the T alpha beta, then you're still left with 4 components. And so this is the total energy and momentum, P alpha. So that is constant, right? And so we have the P and we have the E, right? So all of this is, of course, of fundamental importance because there is an analogy which is quite deep between electromagnetism and gravitation. And both, of course, are fields that are generated by sources. In the case of electromagnetism, the source is the charge. In the case of gravitation, the source is the energy and the momentum, right? But when you think about this source being the energy and the momentum, it means that whatever appears in the equation has a lot more indices as a source term, right? It has 10 components. So that is quite different. And so that means that if you look, again, electromagnetism, you have that the equations for electromagnetism, if you write it in terms of potential, are that this is equal to minus J mu, right? This is in a gauge where D dot A is equal to 0, right? And so maybe you want to make the charge explicit, so you can write it like this here, right? Make the charge. And so this is the electromagnetic case, right? And if you look at the gravity case, then what you do have on this side is G times a T mu nu, right? G times a T mu nu as a source term. Source of the field. And so in electromagnetism, you have only one index, which means that the electromagnetic field is described by an object that should also have only 4 indices, so it's a 4-vector. That is not going to work for gravity. Cannot work because the source for gravity, as we discussed, is an object that has more indices. Right? It has 10 components. 10 components. So if you write the analog of that, right, then for some sort of wave equation, you would write box times some mystery object here is equal to T mu nu, right? And that mystery object has to have 10 components, right? That object, which we could call provisionally as the gravitational field, right, has to have 10 components. Right? And so these 10 components are, of course, very different from what you had in Newtonian gravity, right? Because in Newtonian gravity, you have just a Newtonian potential, which is phi of x. That's a single component, one field. Right? You can describe the whole solar system in terms of just a simple gravitational potential, and if you want to get fancy, you can use Poisson's equation for that, but that's all you have. So it is crucial, therefore, that we realize that when you do have, in fact, energy and momentum, that they're described by an object that has 10 entries, right? And as a result, if you put those into any sort of equation, right, already at the special relativity level, if you wish, right, then you realize that there has to be a lot more fields than there are in the electromagnetic case, right? And so as a result of that, the theory is going to be more complicated, right? Because we have all these indices floating around. It is interesting that Einstein, until about 1912, did not quite realize yet that you had 10 fields. So until about 1912 or so, he was still trying to write a theory of relativity that involved a single scalar field. And it is only after he started to talk to Marcel Grossmann and think about what he had done up to that point that he realized, oh, I think there has to be more components to the field, and the theory is going to be more complicated, right? So this is something that we are already seeing at this level, right? So even before we got started, we already can see that things are going to develop into a direction that will suggest that the equations are not going to be that simple, and that we're going to have lots of indices floating around. Yes?
Did you think that there were contractions that were happening, or did you just not realize?
Of course, yes. The question was whether Einstein thought that there might be contractions at some point. Yes, of course there will be contractions, but nevertheless, if you look at just a fundamental equation before you manipulate any indices by contracting and so forth, it is an inescapable conclusion that the right-hand side of the field equation has to have the T mu nu, and that has 10 entries, 10 independent entries in general, right? And so that means that the gravitational field most likely will also have 10 entries, and then you can do all sorts of contractions on it, and new issues come about, but at least at the beginning, this is what you have, right? So now, it is my plan today to actually finish up special relativity. So there's a few odds and ends that I would like to bring up. And then next time we're going to move on to the general theory. Right? So all the things we do in special relativity, of course, are not just because they're interesting, but because they have relevance for the general theory later on. So we only do the things that are kind of important, which means that we have done a bit of tensor algebra because that's important for general theory, and we also have been talking about the kind of components and ingredients that are essential for later discussion. So now the other thing that we want to talk about briefly is angular momentum and spin. Right, because that will again have some relevance later on, and in any case a discussion of energy and momentum would not be complete, right, already at the Newtonian level if you did not talk about also angular momentum, right? So how do you do that in the relativistic context? Well, again, we start out from the equation, right, of energy momentum conservation, which is d by dx gamma of t beta gamma is equal to 0, right? That was on the blackboard before, so that we know. And now we construct this following object. We construct m gamma alpha beta, right, which is defined as x alpha t beta gamma minus x beta t alpha gamma. Right, so we define an object in this way. And now what we do discover immediately is that if we take the derivative of this thing with respect to x gamma, so if we calculate dm gamma alpha beta with respect to x gamma, then we get the following expression. Right? We want to realize that dx alpha dx beta is equal to delta alpha beta. Right? If you take the derivative of one coordinate with respect to the other, you get a Kronecker delta function. So there's a coordinate right here. So that means that when we take the derivative of this coordinate, we get the Kronecker delta alpha gamma. Right? Well, there's 4 terms there when you take the derivative. There's also a derivative of the t, but the derivative of the t, of course, is 0 because the t is conserved, right? So the derivative of the t does not matter, so the only thing that you get is the term when you take the derivative of this x and the term that you get the derivative of the other x, right? So you get t beta alpha minus t alpha beta, and this is 0 because the thing is symmetric. So this object is conserved. Also, right? And well, because of this combination, you recognize that this is in fact something that should be related to angular momentum, right? The x cross p type of construction, right? So this is something that seems to be useful, and so that means that we can define the angular momentum. Define the angular momentum. So this is like an angular momentum density, the m, right? So we get to define the angular momentum as j alpha beta, right? And we take the integral of the naught component of the m, right? So this is equal to the integral, right, defined as the integral in d3x of m naught alpha beta. And by construction, because of this difference, right, we have that this is also equal to minus j beta alpha. So it is antisymmetric as you would expect for an angular momentum, right? So this is constant. This is constant. Why is it constant? Well, because it's the naught component of a conserved quantity, which is integrated over x. So by the divergence theorem, this is time independent, right? So that means that now we can calculate J23, J31, and J12, and those are the 3 components of the angular momentum. So component 1 of angular momentum, and component 2 of the angular momentum, and component 3 of the angular momentum. 1 or, of course, x, y, and z, right? So if you look at the spatial part, right, this, of course, contains also time parts, right? There is a j naught I, for example. The j naught naught does not exist because it's antisymmetric, so anything along the diagonal is 0, right? But there is a j naught I, okay? Now, so this is the description of angular momentum in the context of special relativity, where you're dealing with 4 vectors and you do this construction that we have just done here. And the other thing that one notices and that you can easily convince yourself, and we will not do it in detail, is that this angular momentum contains both orbital and spin parts. So what is the orbital part and the spin part? Well, the orbital has to do with something going around in an orbit, like a particle. The spin part is the intrinsic part, right? Like spin 1/2 for a quantum mechanical part. Right? The spin part does not depend on the choice of origin, but the orbital part does depend on the choice of origin and coordinate system. So if you do a translation of the coordinate system, right? So if you do a translation where x mu goes into x prime mu, which is x mu plus a mu. So if you do a translation of the coordinate, the orbital part changes. The spin part does not, and it was Pauli who suggested that, in fact, what you should do is for the spin, I need a little bit more space, so let me do it over on this side, that you can define a spin 4 vector. One can define a spin 4 vector, and so that is defined using calling it S alpha, right? And S alpha uses the following combination: 1/2 epsilon alpha beta gamma delta, right? So there has to be a cross product, an epsilon symbol, right? This is this Levi-Civita density in 4 dimensions, right? And then times what? Well, times the angular momentum that we have up here, right? So times this thing here, and so times j beta gamma, right? And then there's one index that's left over, and that last index is saturated with u delta. So u delta is the 4 velocity. 4 velocity, right? So if you take this object really describes the spin. So in other words, if you translate the original coordinate system, this stays the same. Now, what is the 4 velocity? The 4 velocity is, so u alpha, is what you would think as the velocity generalized to 4-dimensional space-time. So the velocity, for example, you can define it by the momentum divided by the mass. So that's how it is defined, right? And we're going to see in a number of cases where this is actually a useful entity to consider. And so as a result, we have that ui, the I component. Now remember that the relativistic momentum is mv times gamma, right? So this is equal to that without the m. So this is gamma times vi. Right? So the spatial components are not quite the velocity, but the velocity times this gamma factor, right? Where gamma is equal to 1 over the square root of 1 minus v squared over c squared, which is 1, right? But there's also an u naught, right? And the u naught is the energy divided by m, so that is just simply gamma. Right? So that's the 4 velocity. And so that is the thing that goes in there, right? And you can calculate, for example, dot product of the 4 velocity with itself, right? Remember, when you do dot products in this way, they're invariant. So they're the same in all coordinate system. And well, you can look it up from there. This is equal to -1. So the 4 velocity squared is always equal to -1. And that is the ingredient that comes in here. And if the particle is at rest, right, for a particle that is at rest, then the ui's are equal to 0, and the u naught is equal to 1. Right, so this. So for a particle at rest, right, v equals 0, which means in a frame that is attached to the particle, then S1 is just J23. and S2 is J31, and S3 is J12. And S0 is 0. S0 is 0. And you can also calculate that U alpha S alpha is always equal to 1. Always equal to 0, sorry, because the knot components subtract out. All right, anyhow, there is this way of describing a spin as something that is separate from the orbital angular momentum, and it has this nice formulation in terms of this Pauli spin vector. Right? So, of course, spin is something that is crucial in quantum mechanics, right? So it's a concept that we want to be able to understand and treat correctly within special and general relativity. But we are also in general relativity, we have the notion of spinning bodies. So for example, recently there were some very accurate experiments that were done to test GR where you had a sphere that was spinning in orbit, right? And so that would be described by this spin vector, right? So you have a satellite, the satellite is in orbit, so it orbits around the Earth, right? And it has orbital angular momentum as a result of that. Right? And the Earth is spinning, so the satellite also is moving in a certain way. And inside that satellite, there is a little sphere, right, about this size that is also spinning, and that is described by this vector S, right? So it's quite relevant for a lot of things, and it's kind of neat that you can do it in this way. So, yes. No particular meaning, but you need to have a knot component. In fact, it's constrained. You see, the dot product is always 0, right? So, in fact, it turns out it has only 3 components, right? Because there's additional constraint. Yeah, so the spin has always 3 components. If the spin all of a sudden had 4 components, then we say, you know, but in quantum mechanics, we thought it was 3. So what's the knot one? Well, the knot one isn't really there because there is this additional constraint. Yeah. So, so we talked a little bit about angular momentum and spin, and now the last thing we want to deal with in the context of special relativity is how you describe a fluid, right? So, relativistic fluid. Well, obviously we don't want to do the general theory because the topic of fluids can be a long and complicated one, so all we want to discuss here is the simplest instance of a fluid, which is a so-called perfect fluid. Right. So a perfect fluid is a fluid that doesn't have viscosities, shears, and so forth, and well, you might think that that's a little bit idealized, but no, that is the kind of fluid that can be used as a lowest order approximation for, in fact, the behavior of matter in the universe. Right? So matter in the universe in a first approximation is described as some sort of fluid and has to be relativistic because otherwise we don't get the right behavior. Right? So the perfect fluid is usually the starting point for cosmology. Right? When you look at equations in cosmology, right, they are treated in a first approximation by the equations for a perfect fluid. So what is this perfect fluid? Well, it is one that it is where it is assumed that the fluid flow is assumed to be isotropic at each point. Right? So that applies well to a number of fluids like water, but certainly also to the behavior of the universe, which is of course made out of particles, but we can think of when you have many particles that we describe it by some sort of fluid. And now it looks the same in all directions, right? Well, of course, the universe is not quite isotropic, but it is isotropic to a good approximation when you look at rather large scales, right? So the assumption that it is isotropic means that it does have a rather simple form for the energy momentum tensor. And so let us look at this fluid, right? and it is described at each location by a velocity, which is described by v. And so we are going to first put ourselves in a rest frame, that is attached to the fluid. So a frame that flows, right, with this liquid, right? And then it means that that particular rest frame is at the reference frame is at rest with the fluid at a given point. And so in that frame, right, which is at rest, right, then we have that the energy momentum tensor has to have a very simple form, right? We denote by the tilde the energy momentum tensor in a frame that is at rest, so it will have components I and j. So we denote that by Tij. And because it is isotropic, the only tensor that will come in at this stage is just delta Ij. Kronecker delta symbol, right? So that is all the tensor structure you can have if it is isotropic, and P is the pressure at that point, right? So in general, it would depend on the point, but here it is just a number that multiplies the Dij. And also, if the fluid if the choice of reference frame is such that it is at rest with the fluid, then in that frame there is no velocity, and so that means that T naught I and Ti naught tilde are supposed to be equal to 0. At rest again, right? And so that leaves as a final entry the T naught naught, right? And you remember the T naught naught is naught component has to do with energy. So in this case, what kind of energy can we have? Well, the only energy we can have is the density, right? So rho. Right. So that was for a frame that is at rest with respect to the fluid, right? And so now we want to write it in a general form, which means the frame is not at rest, right? And so how do we go from a frame that is attached to a particle in the fluid to one that is in the lab and looking at the fluid going by? Well, that is just a Lorentz boost, right? Right, so we just do one of these Lorentz transformations because that's precisely what goes from a frame that is at rest to one that has a velocity v. All right? So that means that x alpha is going to be lambda alpha beta of some velocity of v times this tilde coordinate system, which is the one where the frame is at rest with respect to the fluid. Right? So now in our case, the issue is that T alpha beta is a second rank tensor, right? So that means that we have to have two of those lambda matrices entering into the Lorentz transformation property. So in other words, T alpha beta is going to be equal to the original T tilde through when multiplied by lambda alpha gamma of v, and then lambda beta delta of v times the original T tilde gamma delta, which is the one we have over on this side, right? And so now we look up the form of the Lorentz boost, right? This was given earlier. Right? It was given in the second lecture. We had an explicit form for that Lorentz boost. Do you remember what the form was? Delta Ij for the Ij component, delta Ij plus Vi Vj times gamma minus 1 times, yes. So we look that up, and we do the matrix multiplication, right? We have to do the multiplication twice because it has two indices, so we have to use that matrix twice. And after you've done that little algebra exercise, you find what this T alpha beta looks like. Right, so you find that Tij is equal to P times delta Ij, right, plus P plus rho, times, now the velocities come in, so we have Vi Vj divided by 1 minus V squared. So that's the Tij part. The Ti naught, well, that was 0 to start with, but of course now, because we're multiplying, right, the Ti naught part was 0 here, but now we're multiplying it by these matrices, so it's no longer 0, right? And so that is P plus rho times Vi times 1 minus V squared. Okay. And then we have also the T naught naught. So the T naught naught, that started out to be just rho. Again, now we have to do the matrix multiplication twice, and it becomes rho plus P times V squared divided by 1 minus V squared. Right. So that is what we get. And that, of course, looks ugly, right? Because what we would like to be able is to write a form. What would we like to be able to write a form, right? So this is equivalent to T alpha beta. What we would like to do is to be able to write in a form that involves things that we already introduced before, right? And so we would like to write it as, well, we do know that this is a tensor, right? Which means it should be possible to write it as a linear combination of known tensors, right? And so how many tensors do we know that have two indices, right? Well, the first one is eta alpha beta, right? That is certainly one tensor. So there should be maybe, right, we assume that there should be a part that's proportional to that. That is not the only thing that's going to enter when we write down the energy momentum tensor for a perfect fluid, because what we also can have, right, is some other coefficient, time. What can we use to construct a second rank tensor as well? Derivatives, yes. No, no derivatives at this point. Just think, huh? The velocities, right? But let's use the full velocity, right? So use the U alpha, the one we just discussed, right? U alpha, U beta, very good, okay? And so it should have this structure, because we learned that we construct a tensor by multiplying, doing a direct product of vectors, which is what we do for the second term. And also when you take a linear combination, it's still a tensor, right? So this would be a perfect second rank tensor. And so now we just compare the two. It's enough to compare it by choosing alpha and beta to be naught, for example, and compare it to this. And then choosing alpha to be naught and beta to be I and compare it to the other one. And the answer is that this is P there. And the second term is P plus rho. And so that is the energy momentum tensor for a perfect fluid. You can see that, in fact, it does not contain derivative. It is very simple. It contains just the things that you would think about first, right? Because it contains the eta. Well, that appears everywhere, right? So one piece is proportional to eta. And then it contains a second piece, which is what you would expect, right? Immediately, if you have a fluid, you would think that the velocity would come in. And in fact, it's right here. Right here. This is precisely the velocity term, right? So that's the very simple form. And you know, I'm glad, or maybe it might be a disappointment to you to know that 90% of cosmology nowadays is done with that energy momentum tensor for a perfect fluid, right? Only in some rare instances one wants to get into shears and viscosities and things like that. In a first approximation, this is all that was done. In the early days, right, the first 20, 30 years of cosmology, as far as gravity was concerned, were based on a perfect fluid, right? And so what about P and rho? Well, P is usually a function of rho, right? And you took a whole class on this last quarter, many of you, right? And in that class, you know that that equation is called an equation of state, right? So this is an equation of state. So that means that the P and the rho are generally related. Right? There is an equation of state that relates the P to the rho. So they're usually not independent quantities. And it will be useful, right, to get this out of the way for things that will happen later on, because when we discuss, well, for a while we're not going to look at a perfect fluid at all, because we will be interested in developing the general theory, and then we'll look at things like the Schwarzschild solution and black holes and so forth. But towards the end of the class, we're going to get into cosmology. And so we're going to pick this one up again. And so then we might want to think about what kind of fluids are realistic. And I think the books usually have a much longer discussion that we can do here. But nevertheless, the first type of fluid that we might want to think about is the one that we see when we look outside the window at night, right? And that would be a fluid made out of stars and dust and things like that. And that is non-relativistic. So if you have a fluid that is non-relativistic, so if the effects of relativity are not that important, then P is 0, and you just have a density which is non-zero. So in a non-relativistic fluid, in fact, the P term is quite negligible, right? And if the P term is negligible, then in fact we just have this rho part, right? So it gets even simpler. Now another case which is of interest is one where it is relativistic. And here by relativistic, I mean really relativistic, which means a photon, for example, right? So in the case of a photon, P is equal to 1/3 rho, right? So if you have a relativistic particle, so more appropriately ultra-relativistic, right? A particle that moves either very close to the speed of light or exactly at the speed of light, then P is very close to 1/3 times rho, or exactly 1/3 times rho, as in the case for photons. And of course, photons are very important in cosmology, right? But there are other massless particles that are important in cosmology, namely the neutrinos. Neutrinos are, of course, not exactly massless one-things, but they're very close, so they're well described by an equation of state of this type. So it doesn't have to be just a photon, right? And it turns out that, so you can see already that these two cases can be grouped together into P is W times rho, right, where W is some parameter. W is some parameter. So already the two cases we discussed are W equals 0, right, which is the non-relativistic case, and W equal 1/3. Now it turns out that if you have particles, and this is done in, again, Weinberg has a little discussion of that, it's very easy to show, it just takes half a page, that if you have particles, then W is between 0 and 1/3. So in other words, if you look out for stuff in the universe, and you find that it has an equation of state, which is P equal to 1/2 times rho, then if you do get that 1/2 out of astronomical observation, then it means you discovered something that is not the usual particles, right? And so because if you have real particles, you know, the ones we're familiar with, then it doesn't matter whether fermions or bosons, the upper bound on that W is the 1/3, right? Now it turns out that if W is equal to -1, then you have dark energy. So if W is equal to -1, that's a way of modeling the cosmological constant. So we'll come to that much later in the course. And of course, you can see that if W is equal to -1, then the second term is absent. And you only have the eta alpha beta contribution, right? Interestingly enough, if you have a positive mass density, then the pressure has to be negative, right? Because when W is -1, you get a negative pressure, right? So a negative pressure tends to, make things behave in an odd way. And so dark energy or the cosmological constant is not particles, because particles are not described by a W which is -1. So it has to be something else, and it is what, I'd like to think is just vacuum energy, but that's, of course, a subject that is hotly debated today. And so some people call it quintessence, and, anyhow, we'll come back to that at some later stage. So now, because we are talking about this perfect fluid, we might want to add just a few things. And one of them is that we do have probably an equation of motion somewhere, right? Because we do have the T alpha beta for the perfect fluid. Right, which is that one down there. Right. The other thing that we usually tend to impose is that the fact that the d by dx alpha, right, of T alpha beta is equal to 0. And so that is energy momentum conservation, right? And in fact, it is a local energy momentum conservation, that the energy momentum tensor at each point, right, in space and time should be conserved, right? So this is obviously a function of x. Let's put that in clearly, right? So one might wonder, right, whether when you take the divergence of this thing, you find anything new, or you find something old that has been known since the 16th century, or what it is, right? And so how do you find out if you get something new or something that you already knew? Well, you take that divergence equation and you write it out in components. You write it down in components, and in particular, the question is when you look at the spatial part, whether you get anything new, right? Right? So in components, there's a little bit of algebra everyone needs to do, and so let me write that out, what it is in components. Is there any issue about what any of these things are? No, I remember that ui is equal to gamma times vi, right? And u naught is equal to gamma, right? So we know exactly what all these things are. We know that there is then a pressure and that there is a density as well, and so we can write it out in components. So when you write it out in components, what you will have the density rho, you'll have the pressure p, and you will have the velocity, right? Because the velocity is right here. Okay, so the equations have to contain the velocity, and so you get terms which involve the derivative. How do we get derivative with respect to time? I don't see a derivative with respect to time happening here. Well, of course, we are taking the divergence, right? That contains d by dx and d by dt, right? That contains d by dx and d by dt, so there's going to be terms which involve d by dt. So dv by dt plus v dot derivative with respect to x become gradients, right? So this times that times, again, the velocity, right, is equal, and another term that we get is minus 1 minus v squared divided by p plus rho times the gradient of the pressure plus v times the derivative of the density with respect to time. So that is what the equation that we get in components. And this is, this is something that you find if you pick up a fluid dynamics book. So if you pick up the right volume of Landau-Lifshitz, you will find this equation, and this is the Euler equation. Euler equations for a fluid. Right. So, yes.
This is for which equation? You get beta equals.
The spatial part. The spatial part. Then, of course, there's also the equation for the proper time, right, which I left out. So we've replaced everything. We just have the ordinary time. And so that's the one equation that we can compare directly. And so this is the known equation for a fluid, right? Again, under the same assumptions that we had to start with. There is no shears, no stresses, no viscosity, right? It's the simplest equation. And so Euler actually wrote down this in the 17th century, right? A long time ago. Well, of course, not quite, right? Because it can't be possibly exactly in the same form that Euler wrote it down, right? For the simple reason that this equation is, in fact, relativistic, right? So it's generalization to the relativistic context because you have everywhere these gamma factors, right? You can see one here, 1 minus v squared, right? That's not there. But nevertheless, this is a so-called convective derivative, right? And so you have this same structure. So that means that basically the energy momentum tensor for a perfect fluid can be made to do useful work, right? Not only it is correct under the assumptions that we postulated at the beginning, it does have a simple form because it has to be composed out of 4 vectors and tensors. And also, if you use the fact that energy and momentum have to be conserved, you get a non-trivial equation out of it, right? So you get a non-trivial equation, which is Euler's equation. So that's kind of nice, right? And so you can derive, in fact, the relativistic equations for a fluid just by, we almost could have guessed this, right? You could have guessed this from the beginning, right? That the simplest form of the energy momentum tensor had to be a linear combination of those two things, right? And then if the fluid starts to get complicated, then you have plus dot, 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 right? Other terms. So, all right. So very good. So I think we're ready to leave the subject, right, of fluids. And as I said, we are going to start talking about general relativity next time. And so that leaves us, something about like another half hour. And so we, in this remaining half hour, I would like to talk about something that is still in the context of special relativity, and nevertheless is actually still quite interesting and useful and important, right? And so that would be something that we can extract from properties of the Lorentz group. And so let's talk a little bit about that. We don't have much time, so I'll just give you a course outline of that. So Lorentz group, right? Well, we know, of course, we're talking about these transformations, lambda, alpha, beta, right? That depend on boosts and rotations and so forth, right? And now we do discuss in quantum mechanics, we discuss the rotation group. R, right? The group of rotations, and in 3-dimensional Euclidean space, right? So the rotation group goes from a vector x to a vector r prime, x prime, which is r times x, right? Where this is a 3x3 matrix. Right? 3x3 matrix, right? And you can describe this rotation, for example, in terms of Euler angles. And in quantum mechanics, we have, so why we have here for the vector, we have x prime is equal to r times x. In quantum mechanics, we have a wave function, right? And the component of the wave function is described, is rotated, right, through some matrix, which we call u times psi, right? And this usually has components, and so we write it in this way, right? So U is the rotation matrix on what? Well, of course, not on the x coordinate, right, but on state vectors. right? It's the rotation matrix on state vectors, right? So in quantum mechanics, we have this psi, right? And so the rotation is done on the psi. Now, one of the things that we do learn in the quantum mechanics class is that this rotation has a simple form. Right? That u, right, is equal to e to the I over h bar of alpha dot j. Right? We learned that the rotation is done through the angular momentum matrices. Angular momentum matrices, right? That rotations and angular momenta are closely tied together, right? And remember that. We also learn that the rotations are such that the angular momentum has to satisfy a certain algebra, which is, of course, the algebra of the angular momentum itself, which says that gi jk is equal to I h bar epsilon I jk jk. Right? So we do learn that these angular momenta, of course, have a very specific commutation relation, right? And one of the outcomes of this kind of reasoning and calculations in quantum mechanics, what is the outcome? Is that we discover that only certain values of the spin are allowed, right? That is, we learn that j squared becomes h bar squared times j plus 1, right? And we discover that j can be 0, it can be 1/2, it can be 1, it can be 3/2, and so on. Right? So it is one of the standard exercises of graduate quantum mechanics to actually show that angular momentum only can take on certain values. And that, in fact, you can have spin 1/2, which is legitimate, right, with all its peculiar behavior, right? The fact that the rotation by 2 pi gives -1 and so forth, right? But spin 1/2 is something that comes out of quantum mechanics in a natural way when we consider the angular momentum algebra. And so why do I bring this up here? Well, because the true description of the world is not in terms of rotations in three-dimensional space, right? The correct description after 1905 is in terms of more general rotations, right? Right? So if you bring in special relativity, then x becomes x alpha, right? Which is t and x, right? And so this kind of neat argument that one does in quantum mechanics is okay and is fine, but that somehow does not seem to include in any way special relativity. And special relativity is relevant, right? We think it is relevant for particle physics, it's relevant for quantum mechanics, right? So it should be included, right? So we need to redo this exercise. Right? Need to redo this exercise to determine what? Well, to make sure that we can really only get spin 0 and spin 1/2 and spin 1 and spin 3/2, and that we can't get spin equal to 1/3 all of a sudden, for example, or some other odd thing, right? And that odd thing could be allowed by special relativity, but not allowed by the rotation group in 3 dimensions, right? So that means that we have to start again and do the same kind of argument. And so this was done by Wigner in the 30s and by Pauli. And that means that we write that x prime alpha is equal to lambda alpha beta x beta, which is our standard Lorentz transformation. And then we have psi prime, which is d of lambda times psi. So this is a Lorentz rotation of psi. So this d lambda is like the u here, right? It's called the d matrices. And so we know that they should form a group, so d lambda times d of lambda prime should be the same as d of lambda times lambda prime, right? It should be a group. Right? And for a vector, if we just have a vector here, right, which is a 4-component object, then of course d alpha beta is the same as lambda alpha beta, right? But that's not the only possibility. This side doesn't have to be a 4-vector. It could be a spinor. So it could have 2 spin components, spin up and spin down, right? So there's all sorts of different possibilities. And so we want to find out what these D matrices are, right? And so we want to proceed in analogy to what we do in quantum mechanics, again here for the Lorentz group, right? So in fact, we are doing quantum mechanics again, right? Because we are considering vectors, right? So we are doing special relativity, but also including ingredients of quantum mechanics, which we haven't done so far, right? And so to find something useful, we need to consider infinitesimal transformations. Infinitesimal Lorentz transformation. So that means that lambda, this matrix lambda, is the identity plus something that is small. Right? All right, so we're going to write it in the following way. We're going to write it as lambda alpha beta is equal to the identity. Well, the identity, of course, is the Kronecker symbol. So that's the delta alpha beta, right? And plus a small part, which we denote by omega alpha beta, right? So omega alpha beta in magnitude is much less than 1. It's a small parameter. So this is infinitesimal Lorentz transformation. So that's a transformation where you just rotate the coordinate systems by a tiny bit, which corresponds, in the case of a Lorentz boost, of a small velocity, right? Small velocity increment. So now what we do know is that these lambdas have a certain property, right, which is basically the orthogonality in 4-dimensional Minkowski space-time. That is, we know that lambda alpha gamma, lambda beta delta times eta alpha beta is equal to eta gamma delta, right? That's the requirement that these things be actual rotations, right? It's like an orthogonality constraint. So we stick that in here, and we stick that in there as well. And so we find that delta alpha gamma plus omega alpha gamma, just by substitution, right, times delta beta delta plus omega beta delta, right, and then multiplied by eta alpha beta is equal to eta gamma delta. Now, the first term, of course, is identically satisfied, right? Because this Kronecker delta times that Kronecker delta times that eta gives this eta. Okay, so the 0th order is satisfied. There's also a quadratic term, which is the omega square, which we drop because omega is small. So we only have to concern ourselves with the cross terms. So the cross terms give that omega alpha gamma times delta beta delta times eta alpha beta is equal to that, plus the other cross term, which is this Kronecker times delta. Well, if you stare at it for a second, you can see that all this implies is that omega alpha beta is equal to minus omega beta alpha. That's all that implies. So these infinitesimal deviations from unity have to satisfy this constraint, so the omega has to be an antisymmetric matrix, right? And so that was for the lambda. That was for the lambda, right? Okay, so now what about the d? Well, the d is not going to be the same as the lambda, so let's go over on this side, right? So on this side, when we look at a state vector, then we have that psi prime is equal to d of lambda times psi. Okay, so what is d of lambda? What is d of lambda? Well, that's what we're trying to determine, okay? So if we're dealing with an infinitesimal transformation, then for an infinitesimal transformation, the d of lambda, well, it is the d of 1 plus omega, right? So this is 1 plus omega written as a matrix, right? So it's the d of 1 plus omega, and the d of 1 plus omega, well, it has to start out with 1, right? So if you don't do any rotation, then the d is just the unit matrix, right? And then plus another piece. And so that other piece will depend on this angle, right? This is what determines how much rotation you have. So plus omega alpha beta and times some matrix, sigma alpha beta. Some matrix. So this is like the J. This is like the J. The sigma is like the J. Right? And times 1/2, because omega alpha beta is antisymmetric, right? And we're going to pick the sigma alpha beta also to be antisymmetric, which is sigma alpha beta minus sigma beta alpha. And so we put in the 1/2 because you will always get two terms which are the same. We get sigma 1,3, omega 1,3, and then sigma 3,1, omega 3,1. And they're the same because you can swap indices in the second one twice. And so you get the same result twice. So that's why we put the 1/2, right? So that we count only things once, okay? And so these are going to be some sort of angular momentum matrices, and those are the ones that we want to determine. And so they are the generators of the Lorentz group, so-called generators of the Lorentz group. Now, there's three angular momentum operators, right? And so when we wrote before, U is equal to e to the IOH bar alpha times j, right? That fitted perfectly because there's three angular momentum matrices here, J. And there's also three angles because a rotation can be described by three angles, usually the Euler angles, right? So we know that rotations in three-dimensional space are described by three angles. And that's why there's three J's and everything fits perfectly. That's not going to be true here. Okay, so how many are there of these angles, and therefore how many there are of these other sigma matrices? Okay, well, we are in four-dimensional space-time, right? And we're considering Lorentz transformations, which are rotations. So how many angles does a Lorentz transformation have? 6. Why does it have 6? Because a Lorentz transformation can always be described as an ordinary rotation plus a boost. And the boost has, has three components, right? So there are 6 generators and 6 angles, right? In quotes because they're not quite angles, they're complex, right? And so these 6 angles could be the 3 Euler angles, right? So-called alpha, if you wish, and then the velocity, right? That's a total of 6. Right, so a Lorentz transformation has twice as many parameters as a rotation in real space, right? In fact, if you have, the group that belongs to this is the orthogonal group, right? So this would be the group SOD in d dimensions, and SOD has d times d minus 1 over 2 parameters, which in d equal 4 is actually 6. So there's always a rotation has 6 parameters in four-dimensional space. In fact, it is not SOD, but it is actually SO3, 1 because of the time, but we don't want to get into that. Yes, you had a question.
We could have been able to tell that was the case by looking at the symmetry of omega.
Also, yes. So we have only 6 parameters, so there's going to be 6 of these sigma alpha beta. Okay, so the conclusion is that there are 6 matrices sigma alpha beta. Okay, And what are they? What are they? All right. So now the hard part comes, and the hard part is that you want to do the following. So you want to notice the following, that first of all, if psi is a vector, right? So in other words, if this psi is just like the coordinate, so it is a 4-component vector, then it is easy to write down the transformation property, because then what we call the d of lambda is just the lambda itself, right? And in that case, we have that sigma alpha beta gamma delta, just from the rules of the Lorentz transformation, is equal to delta alpha gamma eta beta delta minus delta beta gamma eta alpha delta. Well, which looks pretty intimidating, right? Because that's these matrices, right? These matrices are 4 by 4 in this case, right? So this is a set of 6 4 by 4 matrices, right? And so one gets this by just using that expression and putting it in the Lorentz transformation product rule. And looks complicated, but in fact it's easy to work out what it is. Because suppose I want to calculate sigma 1, 2, right? So that is, as I said, a 4 by 4 matrix, right? So that means that gamma and delta range from 0 to 3 or 1 to 4, right? But you notice that here almost everything turns out to be 0 most of the time, right? Look, the Kronecker delta does not allow these indices to be different. And the eta also is a diagonal matrix, and its entries are only -1 or +1. So actually, sigma 1, 2, you can figure that out in a minute or so, that this, if you label the components by 0, 1, 2, and 3, then this is 0 everywhere, except it is 1 and -1. So 0 here, 0 here, 0 here. And the 1, 2 is 0, 1, -1, and 0. And then everything else is 0 again. Right? So it looks just like that. There's only 2 entries which are non-zero. And I'll let you guess what the sigma 1, 3 looks like. Okay, the sigma 1, 3 is the same thing, except the -1 goes here at the bottom, and the 1 goes up in the top, and the rest is 0. Okay, so these are actually very simple matrices, right? Very simple matrices. This expression makes it look a lot more complicated than what it is. And so these matrices are the analog of the angular momentum operators, right? And so the next step is to figure out what these commutation relations look like for the sigmas. Right? So in the case of the angular momentum, we have 3 of those. And as I said, they satisfy Ji Jj is equal to IH bar epsilon I Jk Jk, right? So Jx commutator with Jy is equal to IH bar times Jz, right? So that was easy. And here you use, now what you can use is a multiplication rule, by which, so here we want the sigma alpha beta equal to what? And in particular, the commutation relations, right? And so to get the commutation relations, you calculate d of lambda prime, and d of lambda to the minus, or lambda again. You compute the product of 3, I believe in this form, no, lambda to the -1. And because these are all Lorentz transformation, this should be the same as the d that corresponds to the product of lambda times lambda prime times lambda to the -1. So this is what one uses, right? Use this and then do a little bit of algebra, and we won't do that, and just state the result. Okay, state the result is that we get the analog of that commutation relation. Okay, so the analog is that sigma alpha beta commuted with sigma gamma delta. Okay, and so the commutator of one of these sigma with another one, well, we would love this to be just I times another one of these sigmas, and well, it is, but there's lots of terms. So it is eta gamma beta times sigma alpha delta minus eta gamma alpha sigma beta delta plus eta gamma beta times sigma gamma alpha minus eta delta alpha sigma gamma beta. Right, so you get this commutation relation, right? Eta delta alpha, all right? And that is, of course, as ugly as it can be, right? And who's going to be able to sort out what this exactly means, okay? Well, again, it looks a lot worse than what it is, right? It looks a lot worse than what it is because the etas, right? Eta matrix, right? This eta is in fact equal to minus 1, 1, 1, 1, and then 0 everywhere else. So most of the etas are 0, all right? So you can sit down and do a little exercise and compute, for example, sigma 1, 2 commutator with sigma 2, 3. And so these two indices are the same. The beta and the delta are the same. The beta and the delta are the same. So we get an eta 2, 2. So that's 1. This is non-zero. And so here we get sigma, whatever, sigma 1, 3. Plus another 3 terms. No, all the other 3 terms are 0. Okay, because these indices are not the same. The gamma and the alpha are not the same. So in fact, that's all there is to it. Okay, so it looks worse than what it is. And so now you can keep on commuting. And for example, computing, I mean these commutators, sigma 2, 3 with sigma 3, 1. This commutator is equal to sigma 2, 1. And even when you have the etc., right, you see that they're all very simple. They're all very simple. And then, for example, if one of them is a naught, then you have sigma 1, 2, sigma 3 naught commutator. This one is 0. And sigma 1, 3, sigma 3, 0. So 1, 3, 3, 0 is equal to sigma 1, 0. And basically, from the ones I've written, you can reconstruct all the other ones by just swapping indices around. So we basically have all of them. So the commutation relations are actually simple, right? So even though this formula looks like it's quite a handful, right? But most of the terms are 0. All right, well, that clearly looks like the commutation relation for an angular momentum. No way. Right? No way. There's no. There is some similarity, but it doesn't look at this stage like the commutation relation for the angular momentum, because we have all these floating indices that don't seem to follow any particular simple pattern, right? All right. So, but if you're smart, right, and if your name is Pauli and you stare at these things for a few hours and days, then you say, well, look, let me do this clever trick. Okay, let me set A1 to be 1/2 minus, this is a lot of trial and error, as you can imagine, right? So try some linear combination, minus I Of course, it always helps to know what the answer should be, right? Because you have to get back an angular momentum somewhere, because that's how you're going to get spin 1/2 and spin 1, right? So this has to be an angular momentum somewhere. Otherwise, the old quantum mechanics, graduate quantum mechanics argument goes out the window. So he knew that he was trying to get an angular momentum out of it, so he tries all sorts of linear combination. Minus I sigma 2, 3 plus sigma 1, 0. And then define A2 and A3 to be similar. So 1/2 of minus I sigma 3, 1 plus sigma 2, 0. And then 1/2 of minus I sigma 1, 2 plus sigma 3, 0. So you see A2, A1, A2, A3, sigma 1, 0, 2, 0, 3, 0, 2, 3, 3, 1, 1, 2, right? So you can see the pattern. So that's half of them. There's 6 total sigmas, right? There's 6. So we dealt with 3 A's, right? So that's one vector A of matrices, of course. And now we need another one. So we define B1 to be 1/2 times minus I sigma 2, 3 minus sigma 1, 0. Minus. Okay, and then B2 and B3 similarly. So 1/2 minus I sigma 3, 1 minus sigma 2, 0. Right. And then 1/2 minus I sigma 1, 2 minus sigma 3, 0. Okay, and so that's the second vector of matrices B. All right, linear combination, so you should still presumably get some simple commutator. And I'll tell you what the commutator is. The first one is that AI with BJ is always 0. All the A's commute with all the B's, which is nice. Okay, breaks up into 2 separate things. And guess what? AI commutator with AJ is equal to I epsilon ijk AK. And BI BJ is equal to I epsilon ijk BK. Exclamation mark and double exclamation mark. So in other words, what we have discovered and what Pauli discovered is that in fact it breaks up into 2 rotation groups, into 2 angular momentum groups. Right? 2 angular momentum groups, and so what does that imply? Okay, so all this mess has become so much more simple, right? Well, now we have to say something about the eigenvalues. Right? So we can look up these, look up from quantum mechanics class. And so that means that A squared has eigenvalues. What are the eigenvalues of A squared? Well, because the algebra is exactly the same as the angular momentum, the eigenvalues are A times A plus 1, with A equals 0, 1/2, 1, 3/2, and so on. And the eigenvalues of B squared are B times B plus 1, with B equals 0, 1/2, 1 and 3/2, and so on, right? And so that means that all the representations of the Lorentz group are represented by these 2 numbers. So all representations are classified by a pair of these numbers, A and B. Okay. So for example, we can have the 0, 0, and that's a scalar, and it has spin 0. Right? Then we have the 1, 0, and we have the 0, 1. And these are 3-dimensional representations. And so that's spin 1. And then we have the 1, 1, which has dimension 9, and so that is spin 2. The tensor. And also, we have the 0, 1/2, and 1/2, 0, and those are spinors. And they have spin 1/2. So the Dirac field, and we're running out of time, turns out to be the 0, 1/2, comma 1/2, plus the 1/2, comma 0. So, okay, so what has happened? What has happened is that, in fact, the stuff we learned in the quantum mechanics class is still correct. It's still correct. You can't have spin 1/3. Okay, so you still have only spin 1/2, spin 1, spin 3/2, and spin 0. Relativity does not modify that. Even though the group is bigger, right, it's twice as big as it started with, quantum mechanics, and we have used quantum mechanics here, right? In this class now, in this particular lecture, we have talked explicitly about quantum mechanics. Quantum mechanics, when you include special relativity, does not change the conclusion, the fundamental conclusion that in the universe, based on the principles that leads to special relativity, particles can only have spins, which are the ones that we learn in quantum, 1/2 and 1 3/2, and that anything else would not be allowed. Right? If you find a particle that does not fall into these categories, right, then it means that either quantum mechanics is wrong or special relativity is wrong, or both, right? Because if you insist on those, then you can't have anything else, right? So special relativity combined with quantum mechanics still tells you that only certain spins are allowed. And of course, the gravity field we will be talking about will be the tensor, so that will have spin 2. That will have spin 2. All right, well, we're out of time. Maybe there's a question or a comment, right? We managed to finish what I wanted to talk about in special relativity, so any more questions?
What limits it to a spin of 2? Why can't you have a spin of 3?
You can. Yes, it's the dot, dot, dot. Is the dot, dot, dot. So you can have either integer or a half-odd integer spin all the way to infinity, right? So all of those are allowed by these arguments that we talked about today, right? Well, in practice, of course, here we're not going to encounter in the lab or in the universe particles that have very high spin, right? Usually, it's, at least the elementary ones, have spin 1/2, spin 1. The highest spin we encounter for an elementary particle is, of course, the graviton, which is spin 2, which follows in this classification as one of the entries, right? So, yeah, I'm not aware of any fundamental particle that has spin 3. And there have been claims that any theory that has spin greater than 2 is, in fact, inconsistent. But, yeah, there's arguments for that. But that's beyond what we want to talk about here. Any other questions or comments? So next time, general relativity.